Okay, so in the previous class, we are discussing about up to single beam and double beam spectroscopy. So here today we are discussing about selection rules of electronic transition. Okay, selection rules of electron transition. So here, what is the selection rules of electron transition? The absorption of light in the UV visible region. Okay, once I repeat, the absorption of light in the UV and visible range excites the valency electrons in the molecule. The electrons in the molecule will be presenting bonding orbitals. Sigma and pi are called as bonding orbitals, and non-bonding orbital it is denoted by n orbitals, and probably also in anti-bonding orbitals, that is sigma star as well as pi star. By absorption of UV visible radiation of appropriate wavelength, an electron from sigma, pi or n molecular orbital is promoted to an empty sigma star, pi star molecular orbital. Different electronic transitions that can be investigated in a molecule are sigma to sigma star is higher than the pi to pi star and n to sigma star. The energy required to bring about the transition, that is sigma to sigma star, pi to pi star and n to sigma star. Look at this generally. Types of transitions are present. Sigma to sigma star transition. Okay. Then pi to pi star transition. Look at this. So this one is called as sigma to sigma star transition. This is called as pi to pi star transition. Then this one is called as n to sigma star transition. Okay, this once I repeat, wait a minute. Look at this. This is the sigma orbital, pi, n, pi star. This is sigma star. Okay, when the electron in the carbon-carbon single bond components. Okay, suppose carbon-carbon single bond is present. In this condition, the possibility is that the electron is excited toward the sigma to sigma star transition. So this is the sigma, this one is the sigma star. So the the transition is occur in between the sigma and sigma star. It is called as sigma to sigma star transition. Okay. If in which conditions the next one is about pi to pi star transition. Okay, so here look at this. So this is the pi orbital, this is the pi star. So the electron is jump in between the pi to pi star orbital. In the case of the carbon-carbon, it may be having double bond or triple bond. Okay, the carbon-carbon is having the double bond or triple bond, there is a possibility of the electronic transition is takes place in between the pi to pi star orbitals. Okay. Then the next one is about N2 sigma star transition. N2 sigma star transition is group. Sigma bond atom is having the unpaired lone pair of electrons. Okay, so that is mentioned by N. When the transition here, the sigma bond is present, so that's why it is called as N2 sigma star transition. Okay, then next is about N2 pi star transition. If C double bond O. Okay, this is O is oxygen is the heteroatom. It containing the lone pair of electron that is denoted by N, and double bond is indicated by the pi. Then that is called as N2 pi star transition. Okay, once I repeat again, generally these UV visible transitions are four types. One is sigma to sigma star transition. Yes, sigma to sigma star understood. So here in this, in which cases the sigma to sigma star transition is occurred. So if the carbon and another carbon is having the sigma bond, at occurred. Okay. Then the next one is pi to pi star transition. So this is called as pi to pi star transition. So this is the pi orbit. This is the pi star orbit. Okay. So the electronic jump to pi orbitals to pi star excited state. That type of transition is called as pi to pi star transition. So it is occur in the case of the carbon and the carbon is having double bond, or it may be have triple bond. Okay. So double bond or triple bond containing the carbon atoms, this type of transition is occurred. Okay. Then the next transition is N2 sigma star transition. N2 sigma star transition. Zero atom. Sigma star is nothing but sigma bond. Suppose the carbon is bonded with amine group and the nitrogen is having the lone pair of electrons. Okay. So these lone pair of electrons are denoted by the N. Okay. Then these electrons are jumped from N orbitals to sigma star. Then it is called as N2 sigma star. So this one is denoted by N2 sigma star. Then the last one is N2 pi star. How the N2 pi star transition is occur? This heteroatom is bonded group. That means the carbon may be having double bond or triple bond. At that moment, they are attacked with the heteroatom. That heteroatom is having a lone pair of electron. So the excitation is takes place in between the N2 pi star orbital. Okay. So that is called as N2 pi star transition. Okay. So generally in UV visible transitions are four types: sigma to sigma star, pi to pi star, N2 sigma star, and N2 pi star. Okay. Then, according to Zeeman effect, these orbitals are classified into two types: forbidden transitions and allowed transitions. Forbidden transitions and allowed if the transition occurs in normal condition, it is called as allowed transition. If the transition is difficult, it is called as forbidden transition. Okay. UV visible transitions are occur at 154 nanometers. If either CH3, CH3. So the carbon is having the sigma bond. So that's why here the sigma to sigma star transition occurs at 154 nanometers in the UV vacuum UV region. Okay. Similarly, ethylene, that is nothing but CH2 double bond CH2. It is called as ethylene. In ethylene, the pi bond is present. So that's why the pi to pi star transitions are occur at 180 nanometers. Okay. Here, these sigma to sigma star is occur at 154 nanometers. Understood? Okay. So here, therefore, we say that the saturated molecules are simply olefins do not observe regular UV and visible region, and therefore they are colorless. Okay. Two transitions, that is N2 sigma star and pi to pi star transitions are possible in formaldehyde. Okay. In formaldehyde, here the structure is given. In this formaldehyde, the two types of transitions are occurred. One is pi to pi star transition, another one is N to pi star transition. Okay. Next, we are discussing about what is chromophore and what is oxochrome. Look at this. So here the multiple bonds such as carbon-carbon double bond, C double bond O, which are responsible for pi to pi star or in transitions are called chromophore. The multiple bonds such as double bond N double bond N, C double bond S, cyano, nitro, N2 as well as thio and NO are example of other chromophores. These chromophores is in simple molecules absorb at different wavelengths and explain the color components. Okay, and what is a chromophore? So generally the double bond containing systems, they can directly exist the or exhibit the color. Those are called as chromophores. Okay, they absorb the radiation at 400 to 800 mu. Okay, so that's why they exhibit in different colors. Just like it generally the different components are exhibit different types of colors. For example, if the nitro group is present, it is having the yellow color. Okay, if azo group is present, it is having the different color. Okay, so this is regarding for the chromophore. Then what is oxochrome? So this oxochrome, it directly does not exhibit the color, but if it is attached to the moment only, it exhibits the color. So those type of groups are called as oxochrome. Let us see first OH group, or the best example is NH2 group. This NH2 group directly, it is not acting as a chromophore. If it is bonded with a benzene, the carbons are having the double bond. Okay, then it exhibits the color. Okay, directly this NH2 does not exhibit the color, but in the presence of chromophore, it exhibits the color. So that's why it is called as oxochrome. Then next is about what is bathochromic shift and what is hypsochromic shift. So this bathochromic shift, it is called as red shift. Okay. So why it is called as red shift? Okay. Or it is called as low frequency color absorption maximum to longer wavelength. Okay, a shift of absorption maximum to longer wavelength is called as bathochromic shift. Bathochromic shift is called as red shift or low frequency color shift. Okay, generally the alkyls, hydroxyl, alkoxyls, as well as amino groups are attached to chromophore. They are longer wavelength. So that's why it is called as bathochromic shift. Okay. Then next is about hypsochromic shift. So what is hypsochromic shift? Okay. So this hypsochromic shift, it is also called as blue shift, or it is called as high frequency color shift. Okay. Why it is called as high frequency color shift? Okay. Generally in this, the shorter wavelength, that means a shift of absorption maximum to shorter wavelength. Okay. A shift of absorption maximum to shorter wavelength is called as hypsochromic shift. Okay. The next one is about hyperchromic shift. Okay, what is hyperchromic? Is the intensity of absorption is called as hyperchromic shift. Okay, increase the intensity of absorption is called as hyperchromic shift. And what is hypochromic shift? Decrease the intensity of absorption. Decrease the intensity of absorption is called as hypochromic shift. Okay. Then next is about, we can take the some of the conjugated system. In this conjugated system, what is the lambda values? Okay, look at this. So this is 1,3-butadiene. The 1,3-butadiene, it absorbs the radiation at 270 nanometers, and vinyl acetylene, it absorbs the radiation at 219 to 228 nanometers. Just like crotonoldehyde, it is between the 128 into 320, and N-butyl cotonaldehyde, it absorbs the radiation at 219 nanometers. 1-nitro, 1-propane, it absorbs the radiation at 229 to 235 nanometers. Okay, like vice versa. Okay, different wavelengths are absorbed by the different transitions. Let us see about this benzene. Benzene, it absorbs the radiation 203, but it is colorless. In naphthalene, 314 nanometers, it absorbs, it is also a colorless. Anthrazine, it absorbs the radiation at 380 nanometers, and it is buff color. Then naphthalene, it is in the yellow color. Pentacene is having blue color, as well as hexacene is having green color. Okay, so different types of uh, colors are produced. Okay, so here, so in this UV visible region, we are discussing about what is the principle is involved in UV visible spectroscopy, as well as what is the range of the UV visible region, and what is single beam spectroscopy, what is double beam spectroscopy, and we are discussing mainly about the transitions. Okay, generally 4 types of transitions are present. That is sigma to sigma star, pi to pi star, n to sigma star, n to pi star transitions. Then after we are discussing about what is chromophore, what is oxochrome, what is bathochromic shift, what is hypsochromic shift, and what is hyperchromic effect, and what is hypochromic effect. Okay, these terminology goals we are discussed in this topic. Okay, then the next topic is about so the next topic is about metal ions in the biological system. Okay, some of the metal ions are useful in our biological system. Generally, we are know about the sodium, potassium, iron, cobalt, zinc, important in our regular system. Okay, so generally the elements are mainly classified into 2 types. These are essential elements and non-essential elements. Okay, so the elements which are useful very much, these are compulsory essential. Those are called as essential elements, as well as those are in small non-essential. Those are called as non-essential elements. Then, based upon the amount of uses, these are divided into 2 types: macro elements and micro elements. Okay, so macro elements is nothing but the elements which are useful in the larger amount. Those are called as macro elements, and those are requires small amount is those are Okay. Then next, these micro elements, they are find out in the trace amount. Those are called as trace elements. Okay. So this is the normal general classification of metals. Then some of the metals also useful in the biological system. The metals like sodium, potassium, calcium, magnesium, vanadium, chromium, manganese, iron, cobalt, copper, zinc, metals are present in our body due silicon, nitrogen, oxygen, phosphorus, sulfur, cesium, iodine, like 12 elements also very useful to our body. Okay, so here, so let us first discussing about the sodium, potassium elements uses in our body. Okay, so here the concentration of metal ions within the living cell and outside the living cells are different from one another. Okay, in any living cell the concentration of potassium is more than that of the sodium. Okay, the living cells as well as the outside cells. Okay, so in living cells the potassium concentration is very high, and therefore the concentration of sodium ion is more than that of potassium in the outside the living cell. Okay, in living cell the potassium concentration is very more, very high, and in outside the sodium ion concentration is very high. Therefore the concentration of sodium ion is more than that of potassium at outside living cells. Thus, the potassium ions are con- connected with the reactions into cell, whereas the sodium are important for the outside the cell, because the outside the cell the sodium concentration is very high. Inside the cell, the living cell, the potassium ion concentration is very high. Okay. The potassium ions activate the enzymes in the cell, as well as the sodium ions activate the enzymes in outside the cells. Those which are required in very small amount are called, already I told that generally micro elements as well as macro elements. Okay. The next is about bioinorganic chemistry of iron, cobalt as well as zinc. The iron has two oxidation states, that is Fe plus 2 and Fe plus 3. Generally, this iron is very useful in the transport of oxygen and electrons, besides in many other body functions. Okay, iron is mostly present in hemoglobin, myoglobin, and cytochromes. Okay, it is also present in non-heme substances such as proteins and transport. Okay, transferriterins. Generally, the iron it is present in the hemoglobin, myoglobin, cytochromes, as well as non-heme substances like proteins as well as transperitoneins. Okay. The iron protein distribution in human body is illustrated approximately in this table. Generally, look at this uh, hemoglobin, the percentage hemoglobin, it is 65% iron, and the number of irons in the atom. The number of atoms of iron in the molecule is 4, and the oxidation state is +2. The function is oxygen transport. Okay. In hemoglobin, the iron percentage is 65, and 4 iron molecules are present. It is in the Fe+2, as well as it is involved in the oxygen transport. Then the myoglobin, the 6% iron is present. The number of iron atoms is 1, and it is in the form of oxidation state. And what is the function? It can storage the oxygen in muscles. Then transperatin, it is 2% iron is present, and 2 iron molecules are present. It is in the Fe+3 formation, iron in +3 oxidation state. It is useful for the transportation of iron. Then we can take peritin. In peritin, 13% of iron is present, and the number of atoms of iron in the molecule are 4,300, as well as oxidation state is Fe+3. What is the use? Storage of iron in cells. Then we are discussing about cytosine. It is 0.1% of iron is present. 1 molecule of iron is present. It is in maybe Fe+2 or +3 terminal oxidation. Okay. In the presence of oxidation, it is in the +2 or +3 state. Then we are discussing about hemoseridin. In this, iron percentage is 12, and the number of iron molecules, it is 15,000, and oxidation state is +3. It can storage of iron in cells. It can storage the iron in the cells. So this is the function of that one. The enzymes activated by potassium ions are not activated by the sodium ions. Okay. The enzymes activated by potassium ions, those are not activated by the sodium ions, and vice versa. The potassium ions play a significant role in the synthesis of RNA, DNA, and the concentration gradient of potassium and sodium within the cell and outside the cell causes a potential differences between the two sides of the cell membrane. Okay. This potential difference influence the expansion and concentration of muscles. These metal ions are generally present as their chlorides, sodium, potassium, chloride ions help to keep protein molecules in the liquid form and to regulate the blood density and viscosity. The action of retina in the eye is also controlled by the sodium and potassium. Thus, the absence of these ions health issues. Then next we are discussing about the hemoglobin and the myoglobin. These two are intimately related. The myoglobin molecule containing a peptide chain with one hemo group. The molecular weight is 17,000. The peptide chain contains 100 to 160 amino acids. The hemoglobin molecule contains 4 peptide chains. Once I repeat, The myoglobin contains the a peptide chain with one hemo group, and the molecular weight is 17,000. The peptide chain is contain the 100 to 160 amino acids. But in hemoglobin, it contains 4 peptide chains. Each chain contains one hemo group and the molecular weight is 64,454. Iron is present in Fe plus 2. Both of these molecules forms bonds with the oxygen molecule, but their functions are different. Okay, the hemoglobin receives the oxygen from lungs. Okay, once I repeat, the hemoglobin receives the oxygen from the lungs and transport to different tissues of the body. Okay, is transport tissues. The oxygen stored sufficient receives and takes to the lungs. Okay, this is the structure of hemoglobin. So in hemoglobin, the iron in plus 2 oxidation state, it is linked with the porphyrin rings. The hemoglobin readily combines with oxygen to form oxyhemoglobin, and this when treated with glacial acetic acid form a hematin. The chloride of hematin is known as hemin. Its molecular formula is C34. Okay, C34, H32, O4, iron 3, Cl, in which iron atom is ferric state. Cytochromes. These play an important role in the transport of electrons in photosynthesis. These are of three types, A, B, and C. In these, C is the most important. This receives electrons from fusing agent and gives to oxidizing agent. This contains iron in plus 2 and plus 3 oxidation states. The molecular weight is about 12,000. The energy released in the reduction process of oxygen to water by cytochromes is utilized for the digestive process of food. Here the hemoglobin, it is reacted with oxygen, then this 4H plus 4H, it is reacted with oxygen, then it produces water plus energy. The protein containing iron, but no hemo group is present. In these, iron is bonded to sulfur. These are useful for the electron transfer process. Okay, the iron is bonded to sulfur. It is useful for the electron transfer process. So these participate in reduction process also. And the structure can be broadly represented like this. So this is the structure of sulfur. It is bonded with the iron in hemo group. Okay, then ribinodoxin and type of proteins. So these are stores iron in them and supply whenever it is needed. Okay. The next is what is the bioinorganic chemistry of cobalt. Already we know about this cobalt. Okay, generally the vitamin B12 is a cobalt complex. It is this is present in liver. The cobalt in plus 3 oxidation state present as the central metal atom in the complex compound of vitamin B12. Okay, the vitamin B12, it is the cobalt complex. In this, the cobalt in plus 3 oxidation state, it is in octahedral cobalt complex. In the sixth coordination position, the cyano Cn minus is bound to the cobalt. In youth, B12 is present to the extent of 2.5 milligrams, and the B12 is mainly responsible for the synthesis of red blood corpuscles in bone marrow. Okay, generally, what is the main role? This is about red blood corpuscles in the bone marrow. It is for the reason the deficiency of cobalamin, that is B12, in the body leads to anemia. But at the same time, if the B12 present in excessive, it leads to overproduction of red blood cells, and this is known as polycythemia. Okay, if the B12 it is B12 anemia, if the B12 is excess, it is also leads the disease of the polycythemia. Now realize that the zinc is required for all living organisms. In youth, zinc is present in the amount of it is equals to 4 to 6 grams. The two enzymes containing zinc, namely carbonic anhydrase and carboxypeptidase, were discovered in the year of 1940 and 1955 respectively. But today, the more enzymes were known for the containing zinc. Their enzymes are useful for different types of reaction such as alcohol dehydrogenation, transphosphorylation, polymerization of DNA, RNA, as well as, okay. The two important functions are diffused, that is, first one is carbonic anhydrase. So this is present in blood red cells. The molecular weight is 30,000. This is used in hydration reaction of carbon dioxide. The carbon dioxide is reacted with water, then it is converted to carbonic acid. This usually occurs slowly, but the enzymes accelerates the bicarbonate dehydration and the hydration of carbon dioxide reaction. Carboxypeptidase. This is present in pancreas. The molecular weight is 34,600. This enzyme catalyzes the hydrolysis of peptide linkage. Insulin containing zinc. In diabetic patients, the zinc content decreases to 5%. In leukemia patients, it is reduced to 10%. The deficiency and zinc retards the reaction in kidneys as well as in liver. So this leads to retardation of body development. Okay, this is regarding for the some of the elements, metal ions in the biological system. So the syllabus is completed, and all the best for the final exams. Thank you.